Good morning friends. Up to this we discuss about the MCQ question of chapter 11 asked in All India PMT test and also the Neet exam. I think up to 2014 we discussed in earlier. Now today we start with the 2015. The question asked in 2015 is that a photoelectric surface is illuminated by light of wavelength lambda and lambda by 2. If the maximum kinetic energy of emitted photoelectrons in the second case is 3 times that in the first case, the work function of metal is. That means in this numerical, in photoelectric effect, we are radiation of the wavelength lambda and lambda by 2 are incident on a metallic surface. When the wavelength of radiation is lambda, at that time, the emitted photoelectrons with maximum kinetic energy is 3 times of the first case. That means when the wavelength of radiation, incident radiation is lambda, at that time, the maximum kinetic energy is K1. When the wavelength becomes the half lambda by 2 of incident radiation, the maximum kinetic energy of emitted photoelectron becomes 3 times of initial. So what should be the work function of metal? So here we are using the equation of Einstein's photoelectric equation. Maximum kinetic energy is equal to Hf minus Hf0 or Hc upon lambda minus phi. Therefore, kinetic energy Ke, where the K is equal to Hc upon lambda minus phi. In first case, when the wavelength lambda is lambda, at that time the kinetic energy is K1. When the wavelength lambda is equal to lambda by 2, at that time the kinetic energy K2 becomes 3 times of K1. 3 times of K1. So in first case, K1 is equal to Hc upon lambda minus phi. And K2, that is in second case, the maximum kinetic energy, K2 is equal to Hc upon lambda by 2 minus phi. So that's equal to 2 is in denominator comes into the numerator 2Hc upon lambda minus phi. That is the equation 2, that is the equation 1. But we know that final kinetic energy or kinetic energy in second case is 3 times of kinetic energy in first case. Substitute here the value of kinetic energy K2 and K1. K2 is 2Hc upon lambda minus phi is equal to 3 times value of K1. That means the 3Hc upon lambda minus 3 phi. 3 times phi. Therefore, this minus 3 phi taken on left side, so here the 2 phi is equal to this 2Hc upon lambda taken on right becomes negative, therefore Hc upon lambda. Therefore, work function is Hc upon 2 lambda. So that is the answer. Again, when the wavelength of incident radiation is lambda, at that time the maximum kinetic energy of photoelectrons emitted is K1 or the K. Now we decrease the wavelength of incident radiation. That means the lambda by 2. At that time, the kinetic energy of photoelectrons emitted becomes 3 times of initial. Therefore, when the wavelength is lambda, at that time the kinetic energy is K1. And when the lambda becomes the lambda by 2, at that time kinetic energy becomes the 3K1. So by using this concept and Einstein's photoelectric equation, kinetic energy is equal to Hc upon lambda minus phi, we can find out the work function phi is equal to hc upon 2 lambda. After that, a metallic surface is illuminated with radiation of wavelength lambda. The stopping potential is, if the same surface is illuminated with the radiation of wavelength 2 lambda, the stopping potential obtained is V by 4. The threshold wavelength of surface is. So here the same thing again. Lambda is equal, lambda wavelength, at that time the stopping potential V0 is equal to V. Stopping potential is V. And when the wavelength becomes the 2 lambda, at that time the stopping potential becomes the V by 2. So in that case, we have to find out the threshold wavelength of the surface. We have to find out the lambda. So again we know that the Einstein's photoelectric equation, maximum kinetic energy half mv square maximum is equal to hf minus hf0 with hc upon lambda minus hc upon lambda 0 is equal to E into V0. That means maximum kinetic energy is equal to EV0 is equal to hc upon lambda minus hc upon lambda 0. That means the hf minus hf0 or the hf minus phi. We require the stopping potential is given. Therefore, V0 is equal to hc upon E lambda is equal to minus hc upon E lambda 0. Clear this? So here, initially the stopping potential is given the V when the wavelength is lambda. Therefore, first case, stopping potential is V. At that time, the wavelength of incident radiation is lambda. That is our equation 1. In second case, stopping potential becomes 4 times. Stopping potential becomes 4th time. That means the V by 4 is equal to hc upon 2E lambda minus hc upon E lambda 0. That is equation 2. Clear? Okay. So from this equation 4 we taken here. Therefore V is equal to 2hc upon E lambda. This 4 is taken on the right hand side. Therefore 4hc upon 2E lambda minus 4hc upon E lambda 0. So that is our equation number 2. Now the left hand side of equation 1 and 2 are same. Therefore comparing equation 1 and 2. Compare 1 and 2. Therefore we obtain hc upon E lambda minus hc upon E lambda 0 is equal to 2hc upon E lambda minus 4hc upon E lambda 0. So as we simplify, we obtain threshold wavelength is 3 times of the wavelength of incident radiation. 3 times of lambda. Because the HCLC is common, that is taken out or cancel out, and we simplify one side the term with lambda and other side terms with lambda 0. Therefore, by simplifying this, we obtain the threshold wavelength of a given metal is lambda 0 is equal to 3 lambda. Clear? Okay. Now, next, asked in 2016, an electron of mass m and a photon have the same energy. The ratio of de Broglie wavelength associated with them is. Now we know that the de Broglie wavelength of an electron, lambda E is equal to H upon 2. Here the energy of photon and electron are given, that means there is the E. Therefore, H upon under root of 2me. So that is the wavelength of the electron. But we know that E is equal to HF. E is equal to HF. Therefore, for photon has also the same energy, so we can add the Hc upon lambda p. Hc upon lambda p. Therefore, the wavelength of photon lambda p is equal to Hc upon p. Hc upon. Now taking the ratio of lambda E upon lambda p. Lambda E already we obtained H upon under root of 2me. Now, divided by the value of lambda p, Hc upon E, that means the E upon Hc. Reciprocally multiply. Hh cancel. Here 1 times E cancel. Therefore, we obtain 1 upon C. Here under root of for the E upon 2m raised to half. Therefore, ratio of wavelength of electron to the wavelength of photon is 1 upon C into bracket E upon 2m raised to half. Again, the de Broglie wavelength of electron is H upon momentum P. Here the momentum of electron having the energy is under root of 2me. Therefore, H upon under root of 2me. Now, the photon has also the same energy. The characteristic of photon is equal to HF, or the E is equal to Hc upon lambda. Therefore, Hc upon lambda p. Therefore, the de Broglie wavelength of photon lambda p is equal to Hc upon p. Now, taking the ratio of wavelength of electron to the wavelength of proton. So, we obtain 1 upon C into bracket E upon 2m raised to half. So that is our answer. Answer is our C. Answer is D. Now next, asked in 2016, when the cathode C of photocell is incident with the photon of 5 electron volt energy, the maximum kinetic energy of the electrons emitted is 2 electron volt. Here the photocell here is incident with the photon, but the incident energy is 5 electron volt. At that time, the maximum kinetic energy of the electrons emitted is 2e. For which value of stopping potential on anode A, the photon incident with energy of 6 electron volt, number of the electron reaching to anode will becomes 0. So we are using the equation of Einstein's photoelectric equation. Maximum kinetic energy is equal to Hf minus phi 0. First we find out what is the work function. Therefore, kinetic energy K is equal to Hf minus phi 0. Now initially, the energy of the incident photon is given the 5 electron volt. Kinetic energy is 2 electron volt. So work function of a given metal is phi minus 2 is equal to 3 electron volt. Is the 3 electron volt. Now, we are using this equation. EV0 is equal to Hf minus phi 0. Now the photon with the energy 6 electron volt incident. Work function already we find out 3 electron volt. So that is the EV0. Therefore we obtain there is the 3 electron volt is equal to EV0. Therefore stopping potential is 3 volt. That is the value of stopping potential. But now listen, read the question carefully. We have to find out which value of stopping potential on anode with respect to cathode. Not we have to find out the stopping potential. That means the potential difference between the anode and cathode. We have to find out what should be the value of potential on anode with respect to cathode. Therefore, here we obtain the stopping potential. That means the potential difference between the cathode and anode. That is the Vc minus Va is equal to 3. Hence, you consider the voltage on cathode is 0. Minus Va is equal to 3 volt. Therefore, Va is equal to minus 3 volt. That is the value of potential on anode of a photocell. So most of the students can write down directly value of stopping potential 3 volt, but that is the wrong. Because here there is the mention that for which value of stopping potential on anode, not the way to find out only the value of stopping potential. Again, this photocell is incident with the photon of 5 electron volt energy. At that time, the maximum kinetic energy is 2 electron volt. By using this concept, first we find out what is the wave function of a given metal. So first we find out the wave function. Now, the energy of incident photon is 6 electron volt. At that time, what is the first find out what is the value of stopping potential? After that, what is the value of stopping potential on anode A to stop this number of electron reaching to the anode? Therefore, EV0 is equal to HF minus phi 0. We find out the V0 and then we find out the potential on anode of a photocell. Now, next question in 2017. If the mass of deuterium is 1.7 into 10 is to minus 27 kg, then de Broglie wavelength of neutron of energy 3 electron volt is. We have to find out the de Broglie wavelength for neutron having the mass is given 1.7 into 10 is to minus 27 kg. Energy of the neutron is given E is equal to 3 electron volt. We require the de Broglie wavelength. For that purpose, the de Broglie wavelength lambda is equal to h upon under root of 2m. h આપણે આપેલો છે 6.6 into 10 is to minus 34. વર્ગમૂળની અંદર d એને ગુણ્યા 2 multiplied by the mass of the neutron 1.7 into 10 is to minus 27 and energy of neutron 3 electron volt 3. Now convert into joule, so 1.6 into 10 is to minus 19, so that much joule. Yet we simplified, so we obtain the wavelength of neutron is 1.65 into 10 is to minus 11 meter. Again, the mass of the neutron is given 1.7 into 10 is to minus 27 and energy of the neutron is given the 3 electron volt. What is the de Broglie wavelength of neutron? So we know the equation lambda is equal to h upon under root of 2me. Now we substitute the value. H Planck's constant, its value is 6.6 into 10 is to minus 34 divided by under root of 2 into m, mass of the neutron 1.7 into 10 is to minus 7, energy 3 electron volt 3, convert into joule, so into 1.6 into 10 is to minus 9. If we simplify, we obtain the wavelength of neutron is 1.65 into 10 is to minus 11 meter. Clear? Very easy numerical. Okay. Now next, also asked in 2017, in experiment of photoelectric effect, the stopping potential are V1 and V2 with incident light of wavelength lambda and lambda by 2. That means when the light of wavelength lambda is incident, stopping potential is V1. when the light of wavelength lambda by 2 is incident, stopping potential is V2. The relation between the V1 and V2 is, what is the relation of the following? Either the V2 is greater than 2V1, either the V2 is less than V1, or V2 is equal to twice V1 and V1 less than V2 less than 2V1. Now, for that purpose, we know that the Einstein's photoelectric equation EV is equal to Hc upon lambda minus phi. Therefore, EV0 is equal to Hc upon lambda minus phi. Therefore, the stopping potential V0 is equal to Hc upon E lambda minus phi upon E. Now, this value, when the wavelength is lambda, at that time the stopping potential is given the V1. Therefore, V1 is equal to Hc upon E lambda minus phi upon E. So, from this equation, Hc upon E lambda is equal to V1 plus phi upon E, equation 1. We require the relation, right? When the V0 at the time, when the wavelength is lambda, at the time the stopping potential is V1. Now, for second case, lambda by 2 wavelength, at that time the stopping potential is V. Therefore, V2 plus phi upon E is equal to 2Hc upon E lambda. Because in this case, this equation, it is substituted the V2, at that time the lambda is equal to lambda by 2. So, lambda by 2 is in denominator of denominator, comes into the numerator, therefore 2Hc upon E lambda is equal to V2 plus phi. Clear this? Oh. So, here the 2Hc upon E lambda, here the Hc upon lambda, substitute the value of Hc upon lambda here. Substitute equation 1. Therefore, V2 plus phi upon E is equal to Hc upon E lambda. Hc upon E lambda is V1 plus phi upon E. V1 plus phi upon E. Therefore, V2 is equal to 2V1 plus phi upon E. Because on the right hand side there is the 2 times of phi upon E, here the 1 times phi upon E taken on the right hand side becomes the negative. Therefore, V2 is equal to 2V1 plus phi upon E. Therefore, V2 is greater than 2V1. There is our answer. There is the relation between V1 and V2. Again, when the wavelength of incident light is lambda, at that time the stopping potential is V1. And when the wavelength, incident wavelength is lambda by 2, at that time the stopping potential is V2. Now, what is the relation between this V1 and V2? So, from Einstein's photoelectric equation, EV0 is equal to Hc upon lambda minus phi. Therefore, V0 is equal to Hc upon lambda, Hc upon E lambda minus phi upon E. Therefore, V0 is equal to this equation. Therefore, when the wavelength is lambda, potential is V1. Therefore, V1 is equal to Hc upon E lambda minus phi. Now, from this equation, Hc upon E lambda is equal to V1 plus phi. Now, in second case, wavelength is lambda by 2, potential is V2. Therefore, V2 plus phi E is equal to Hc upon E lambda. Here we substitute the value of Hc upon lambda of equation 1. So, we obtain this relation, V2 is equal to 2V1 plus phi upon E. That means the V2 is greater than 2V1. Now, next, for a metal plate, threshold frequency is F0. When the radiation of 2F0 is incident on a metal, maximum velocity of the photoelectron emitted is V1. And when the frequency of the incident radiation is phi f0, the maximum velocity of the photoelectrons emitted is V. What is the ratio of the V1 upon V2? For that purpose, here we are using the Einstein's photoelectric equation. Half mp square maximum or the kinetic energy is equal to hf minus hf0 or the phi. When the frequency is 2 hf0, when the frequency is 2 hf0, or in other words, hf minus hf0. When the frequency is 2 hf0, at that time the maximum kinetic energy or the maximum velocity is v1. And when the frequency is phi f0, at that time the velocity is v. Clear this? Okay. Therefore, half mv square is equal to hf minus phi, for the hf 0. That is our first equation. Now, frequency is 2f0. So simplification is hf0, that is our equation 1. Half mv square maximum. And half mv2 square, at that time the frequency is phi f0, therefore phi hf0 minus hf0, that means the 4 hf0. That is equation 2. Now we are taking the ratio, that is the half m v1 square upon half m v2 square, that is cancel, is equal to hf0 upon 4 hf0. Therefore, v1 square upon v2 square is equal to 1 by 4. Therefore, v1 upon v2 is equal to 1 by 2. Now listen, from Einstein's equation, maximum kinetic energy is equal to hf minus phi. Threshold frequency is f0, therefore instead of the phi, we substitute the hf0, therefore hf minus hf0. Therefore half mv square variable is equal to, here the frequency is 2f0, therefore 2hf0 minus hf0, subtraction is hf0. That is our equation 1. Similarly, maximum speed is v2 square when the phi f0 energy frequency is phi f0. Therefore, half mv2 square is equal to phi f0 minus hf0 in this equation. Therefore, 4 f0. Taking the ratio of this equation 1 and 2, half m cancel. v1 square upon v2 square is equal to hf0 upon 4 hf0. Therefore, v1 square upon v2 square is equal to 1 by 4. Therefore, v1 upon v2 is equal to 1 by 2. Clear this? Okay. Now the next, electron of mass m and initial velocity v is equal to v0i. Enter in electric field E is equal to minus E0i. At time t is equal to 0, the de Broglie wavelength of electron is lambda 0. Then at time t, its de Broglie wavelength is 1. Right? For that purpose here, the V is given, the V0i, electric field is given minus E0i. Therefore, F is equal to ma, or the A is equal to F upon A. F upon M. Here, there is the minus E E0 I upon, there is the M. So acceleration is E0 upon M. There is the value of acceleration. Now from equation of motion. for constant accelerated motion. Now listen this me. Now listen here, the velocity is given v0I in positive x direction. Electric field is in negative x direction, minus z0I. Therefore, acceleration is F upon it. Now, uniform electric field, the force act on an electron is equal to charge into electric field. So here the charge of an electron is minus E. Here electric field is minus E0I upon it. Therefore, E is 0 upon m into I. That is the acceleration of an electron in electric field. Again, the acceleration of an electron is equal to F upon m. F, force acting charge of electron into electric field upon it. Therefore, minus E into minus is 0I. Therefore, E is 0 upon m into I. That's the acceleration. Acceleration of an electron in positive x direction. Now, equation of motion, V is equal to V0 plus A. V0 plus A. Substitute the value of A. Therefore, velocity is equal to V0 plus E is 0 upon m into D. Therefore, de Broglie wavelength lambda is equal to h upon mv. H upon mv. Here we substitute the value. Therefore, de Broglie wavelength lambda is equal to h upon m into velocity v0 plus e0 upon m into d. So we can write it this way. Here v0 is taken common from the bracket, from the denominator. mv0 is equal to 1 plus e0 upon mv0t. Now we know that wavelength lambda is equal to h upon mv. Now h upon mv0 is equal to lambda 0. Therefore, we can write lambda is equal to, instead of this, there is the lambda 0 upon 1 plus e0 upon mv0 into d. Lambda 0 upon 1 plus E0t upon mv0. So that is the de Broglie wavelength of an electron. Again, the electron of mass m and initial velocity v is equal to v0I. Enter in uniform electric field E is equal to minus E0I. At time t is equal to 0, de Broglie wavelength is lambda 0. And at time t, what is its de Broglie wavelength? Therefore, here the electric field is given in charge of an electron. Therefore, the acceleration of an electron is equal to F upon m. So, E is 0 upon m in positive x direction. Now, from equation of motion, V is equal to V0 plus AD. So, here we substitute the value of acceleration. V is equal to V0 plus E is 0 upon m into t. Therefore, de Broglie wavelength lambda is equal to h upon momentum. That means the h upon m. Substitute the value of v. Therefore, lambda is equal to h upon m into bracket v0 plus ev0 upon m into t. Now, v0 is taken common from the bracket. Therefore, h upon mv0 into bracket 1 plus e is 0 upon mv0 into t. But we know that h upon mv0, that is the de Broglie wavelength of an electron at time t is equal to 0. Clear? Therefore, answer, the de Broglie wavelength of an electron at time t is lambda is equal to lambda 0 upon 1 plus E is 0 upon mv0 into T. Okay. Okay, after that, the next question asked in 2019. An electron is accelerated through a potential difference of 10,000 volt. Its de Broglie wavelength is. Here, the potential is given, the V is equal to 10 to 4 volt. V equals the de Broglie wavelength level. Now we know that the equation of the de Broglie wavelength is h upon under root of 2m value of h 6.6 into 10 minus 34 upon under root of electron having the mass is 9.1 into 10 minus 31. Here, charge of an electron 1.6, 10 is to minus 19 into 10 is to 4, that is the applied potential. It is simplified, we obtain the answer is 12.2 into 10 is to minus 12 meter. That is the de Broglie wavelength of an electron that is accelerated at the potential difference of the 10,000 volt. Where is the numerical? Only we have to apply the equation lambda is equal to h upon under root of 2m. Substitute the value, we obtain the answer is 12.2 into 10 is to minus 12 meter. Right?